Welcome to a new session. So, in our last session, we studied all about AVL tree, and now we know that AVL tree is actually a binary search tree. But why do we need to study this? Because it is a kind of a special binary search tree. It is a self-balancing binary search tree. It is always balanced. And what does balanced binary search tree mean? Balanced binary search tree means that the difference between left and right subtree is at most 1. That can be 1 or 0. By 0 means equal, left subtree and right subtree. And it is said to be self-balancing binary search tree. That means when you insert new node in the tree, if that new node makes the tree unbalanced, then it automatically make these rotations and make it balanced. For that reason, we call it self-balancing. And we need these methods to achieve this goal. So, in last session, I took part of a tree that was containing the 3 nodes just to explain what rotation means and how you rotate that. And there I explained that, well, when a tree is left execute, that means it is left heavy or left scenario, you rotate this to the right. You like take number 30 and move it down. But when writing code, you just do not say move it down. Writing a program or writing code is a step-by-step approach that follows a reason, a logic, or it is an algorithmic approach. So that means that you just cannot make this the child of this node. You consider different scenarios and different edge cases, and then you start writing your program. Let's see how that works, how that looks to write the code for all these operations. So if you have this kind of tree and you need to rotate this to the right side, as I said, it is part of a tree. It is not the whole tree. A whole tree can have as many nodes as possible as we need to have in that tree. But when we make the rotations, we only consider 3 nodes. So this means that there is a possibility of this node having a right child. That means there can be a subtree here. Also, there can be a subtree here, like this. So if they have subtrees like this, so but now look, how do you move number 30 down? If you move number 30 down and make it child of 20, so you see that here this node already has a left and right child. Also, this node already has a left and right child. So when you move this down here, you should be taking care of these subtrees also. And that is what makes it to be very careful when you are making these rotations. So now let's see how we can implement this. So let me give this node a name. I think that way it is easier to explain this. So I gave this node the current root node as y. So when I need to move y down here, so I'm making this node the child of this node. So that means we are losing this connection. And if we lose this connection, then it is the current, like after it becomes the child, so it should be the root. And if we lose the connection to this root, that means we lose the connection to the whole tree. So that is not a good approach. Before moving this down, we need to have stored this root somewhere in a separate variable. I call that like an, you give it a name, any name that you want. I give it a name x. So I'm saying that first I need to keep that in the x. I'm saying that how can I get that? So I'm saying that x equals y dot left. Y dot left points to this one. So I store that here, y dot left. So now I have access to this node using this one. And now when I move this one here, so that means I already have access to this one. And also, when you move this down, so if you put number 30 here, so it already has a left and right child. So what do you do with this subtree? You just cannot lose this subtree. Let me give it like T2. T2 is a very common name that in many resources you see that. Otherwise, it is up to you. You can give it any name that you want. It just shows it as a subtree or second subtree, something like that. But you can give any name that you like. So I just give this T2. So like we should not lose this subtree also. For that reason, in order to not lose connection to this, so before moving number 30 down here, the node y, we should store this in a separate variable also. So I can say that I can store that in a separate variable and name it T2. I'm saying T2 equals, so it is x dot right. Okay, x dot right, because I access to this subtrees now through this x, because I have stored this address using the y dot left here. So now I have access to both of them. And now when I move this down here, so now let's move it down here. So now, okay, so I moved number 30 down here. So it already has a left subtree already. So that is lost. We don't need that anymore. So it is our y. So here we have another subtree that was T2. So now where we how do we access to this subtree, to this T2? So right now you see that this node already has a right subtree, and this T2 was the right subtree of this node. But at this point, should we make it another right subtree or left subtree to this one? So as far as it was a binary search tree, you already know that all the node to the left side is smaller than the node to the right side. So if that is the case, so number 30 was here. That means whatever is under this left subtree, that is smaller than this. For that reason, this number 2 becomes the left child of this node. Because that is smaller than this one. See, it was this T2 was the right child of 20 or x. But when we move y down here, so this y is greater than this one. So that means if all this tree is smaller than this one, so that should be like its left subtree. So like this we can keep our tree balanced. Now let's see how we can actually write the code for these operations. So uh, we create a new project. Actually, at first I started to write the code from scratch and record all the steps, but it was becoming very long video, and that was difficult to watch. So I wrote the code before recording. Now I will explain that. So for these operations, we need to define these methods. We need to have this height method, the balance method, the right rotate, left rotate, and insert method. So the height is very easy. So in general, when you want to implement this, so you need to have at least two classes. One class to represent the nodes, node class, and here you see that your node has 4 different properties. And one thing more that I need to point out, I feel a little sick. It is very cold. I think I have flu. For that reason my sound is not good at some point, so I apologize for that. I hope until the next session it becomes better. So see, your node has a key property, that means the value or data, which is like 10, 20, and 30. It has left and right properties. Every node has left and right properties. And every node has the height properties, because height is very important when you work with binary search tree and AVL tree. For that reason, we always keep updated that property. And then we have another class, the tree class, which has one important property, that is root. Because using this root, we access the tree. So getting a height of every node is very simple. You just need to get this property, and you can access this one through the object of this node. So if you have an object of the node, and then easily you can say n or node dot height. So there you only check one edge case. If the node is null, that means the tree is empty, so it returns 0. But if there was some elements, then you need to directly get the height of that node, and you say that n dot height, so you can get the height of this node, and by default it is initialized to 1. But every time that a new node is inserted, it is getting updated. You need one more method to get the balance factor. That means you need to get the difference between the left subtree and the right subtree, and based on this difference you can check if it is balanced or not. If this difference is out of the range -1, 0, and 1, that means the tree is unbalanced. So if that was unbalanced, then you start making your rotations. So here is right rotation. See, here is the whole process that I just explained here. So when you found a node where it was unbalanced, for example at this part, when you come to a tree like this, so now let's see what does it mean like unbalanced. So you get the balance factor of this node. Balance factor of this node should be the height of left branch plus minus the height of right branch. So height of its left is 1, and 1, 2, and the right is null. So let me write that here, for example. So there's node number 30. The left is this subtree, and the height of this is only 1 minus the height of right subtree. So you see there is no right subtree, that means null, and the value of null, I said that we assign -1. So now 1 minus -1, it is 2. That means it is out of this range. Out of this range, -1, 0, and 1. It is out of this range. So now we know that it is unbalanced. And now, how should we recognize if we need to make a right rotation or left rotation? So again, it is something very logical. So when the result becomes positive and when it becomes negative, it becomes positive when the left side is bigger, greater. For example, if there you have 4 and on the right side you have, for example, 2, 4 minus 2 equals 2. You get a positive number. So that means the left is bigger. And when you have a negative value, for example, you have 1 minus 3, the result is -2. So at that time you know that, well, the right subtree is longer than the left subtree. So that means it is right skewed. Based on this result, you make your decision. So now let's see how this rotation works. So on number 30, you found that, well, it is unbalanced because it is 2. Then you pass this node to this method, right rotate. And based on this value, you need to rotate it to the right side. So you have given the name of this road as y. So see, before losing this connection, first we keep that in the x. Node x equals y dot left, and node t2, this subtree, we keep that here, x dot right, and then we make our rotation. So then we can say that, well, now x dot right equals to y, and y dot left equals to t2. So we made the rotation. And when you made the rotation, now you need to update the height of these two nodes. So again, you need to, for example, you need to see the height of this one and the height of this one. So the height is the longer path from that node until the leaf. So you check its right and left, and you get which one is the longer one. For that reason, we have used the built-in method max. So we give the left side and the right side. For example, when you're checking for the y, which it is here, or when you're checking for the x, which is here. So you give the left value and the right value, and then it gets the longer one. But here you see a +1. What does that mean? For example, that means if you consider this x, so this is the left subtree and this is the right subtree. So when you get the maximum between these two, that means it doesn't include this part, this node, this edge. For that reason, you make a 1 plus. No matter if it is the left one or the right one. If it is the left one, you need to include this one at the end. If it is the right one, then you need to include this one. For that reason, you make a plus 1. So that's how you make the right rotation. And the left rotation is exactly the same process. So you should be able to know that these two are the same thing. And now here is how you insert new node and how this AVL tree is self-balancing. So there are 3 important points that here you should know. First, you should be able to perform normal binary search tree insertion. So for this part, I hope you already know that, but if you have some questions, once review how to insert new node in the binary search tree. Now, update the height. When you insert a new node, so you need to update the height of the nodes. And then you need to check the balance factor. You need to get the balance factor. And based on this balance, you can recognize if you need to make a left rotation or a right rotation. And there are 4 scenarios. You already know that, all those 4 scenarios. So the first scenario can be LL case or left case. That means both the node are inserted to the left side. That means there's a left skewed. So how do you recognize that? You say if balance is greater than 1, so you already know that from here. If balance is greater than 1, that means the left subtree should be bigger than the right subtree. That is when the balance is greater than 1. So at least you know that it is going to the left side of the current node. But the next step, how do you recognize that part? That is an important logical step. So the first node you could recognize based on the balance factor. So you say that if the balance factor is greater than 1, so if it is greater than 1, that means at least you know that the left subtree is longer. So that means it should be at first left skewed. And then you should be checked is it left or left right? So that is when you check this part. Key is less than node.left key. So you came to the left side and you say that key should be less than node.left key. So if this is less than the left, so that means that is also inserted to the left side. Because if it was greater than this, so that should be inserted to the right side. But it is less than that, so that is again inserted to the left side. So now you know that there is left. And then you call the right rotate method. Same with the right scenario. You check that the balance is less than -1. It can be like -1, -2, -3. That means the right side is bigger than the left side. because the result is minus. And left right, same thing, right left, same thing. You need to visually see them, check them. That is how you recognize which kind of rotation you need, and then you call your left or right rotation method. So I hope it was clear enough that you get the idea of how these things work. I know at first it looks quite complicated and difficult, but it is not very difficult as it looks. The whole point is that you need to visually understand the problem, because if you visually understand this problem, it is very easy to understand these parts. For example, to see this part. If, for example, this part, if balance is less than -1 and key is greater than node.write.key. So if you don't understand these pictures from this code, it is really difficult to understand them. For that reason, always check, for example, is it less than this or it is greater than this? So when you understand this in pictures, then easily you can analyze the code. So for now, I think it is enough explanation. Once go through this yourself, check everything. If you understand, that's fine. If not, if there was a question, add your question in the comment, or if you have any more comments or suggestions or recommendations, please add them in the comment section. I will take care of them in the next sessions. So until our next lesson, have a nice time, everyone.